We can build robots that perform backflips, but ask one to grab a specific pair of pliers off a messy workbench, it completely freezes. The hardware is agile, but the cognitive software trying to make sense of a chaotic physical space collapses. This is the sim-to-real gap. Wiring a general-purpose AI like Gemini 3.0 Flash directly into a physical robot often results in failure. These models frequently hallucinate objects or misjudge physical boundaries because they lack native spatial logic for unstructured environments. Google DeepMind's April 2026 release of Gemini Robotics ER 1.6 addresses this disconnect. It is a specialized embodied reasoning layer designed to process the physical world. ER 1.6 is the high-level brain in a dual model stack. It handles natural language and spatial reasoning in the top layer. A separate bottom model manages motor control. It translates human instructions into commands, pushing them down to trigger movement. Connecting understanding to movement requires the AI to process the physical world in 3 distinct phases: perceive, execute, and verify. The first step is perception. Before the robot moves, the reasoning brain must accurately map the environment without inventing objects that don't exist. ER 1.6 uses a mechanism called pointing to accomplish this. By overlaying visual pointers on its camera feed, the model detects and counts items while establishing relational logic, such as identifying the smallest object in a group. In a cluttered workshop benchmark, this allowed the model to correctly identify 2 hammers and 6 pairs of pliers. It successfully ignored absent items like a wheelbarrow or a drill, tools that frequently cause earlier models to hallucinate. Tying logic to exact visual coordinates also creates a framework for safety. It allows the model to enforce physical constraints before any movement begins. Under DeepMind's Asimov benchmark, the model evaluates edge cases. For instance, when asked to set down a cup, it explicitly refuses to place it near a table edge where it could fall. By anchoring cognitive logic to physical coordinates through pointing, ER 1.6 establishes a reliable starting point for real-world interaction. Once the space is mapped, the robot moves to the second phase, execution. In industrial settings, this means interacting with interfaces built for humans. This is already active in the field. ER 1.6 powers the Boston Dynamics Spot robot via the Orbit AI/VI platform, allowing it to autonomously patrol industrial facilities. A major hurdle for these patrols is reading analog gauges and thermometers. In these environments, instruments are often viewed from distorted angles or in poor lighting. ER 1.6 solves this through agentic vision. The robot zooms in on the target, executes code to mathematically correct the camera's perspective, and applies its world knowledge to interpret the dial. This chart highlights the impact of that process. While the previous ER 1.5 scored just 23% on instrument reading, ER 1.6 with agentic vision reaches 93%. Equipped with agentic vision, the system actively solves spatial problems in the field, reaching sub-tick accuracy on dials that were previously unreadable. The final step is verification. How does an autonomous agent actually confirm its physical action was a success? ER 1.6 uses multi-view success detection, fusing real-time video feeds from both overhead and wrist-mounted cameras. If the robot attempts to put a pen into a holder, it cross-references these angles to confirm the pen is inside rather than dropped behind it. This allows it to see through the physical occlusions that blind single-view systems. This verification loop gives the robot the ability to recognize failure and independently decide to retry a task without human intervention. ER 1.6 signals a shift in focus toward the high-level cognitive software required to navigate messy, real-world environments. True end-to-end embodiment, where one network handles everything from vision to motor torque, is still a future milestone. ER 1.6 currently relies on those separate, low-level controllers for movement. DeepMind's leadership, including Demis Hassabis, views this dual-stack approach as a pragmatic path forward, delivering tangible gains on real hardware today. This trajectory begins with industrial inspection, but the safety and success detection features point toward future applications in logistics, elder care, and hazardous environments. By giving robots a specialized mechanism to reason, the gap between simulation and the real world has started to close, expanding the possibilities for genuine physical autonomy.